a system is said to be absolutely stable if the system is stable for all the values of variable parameter k from 0 to infinity. So generally in any system, k is taken as a variable parameter. Therefore, for all the values of k, if the system is stable, then we say system is absolutely stable system. So not only the variable parameter k, any other parameter. For example, if we take g of s, k by 1 plus st. So if k is given to you, if you know the k value, if the t is a variable parameter, for all the values of t, system must be stable. Then only we say this system is absolutely stable system. Similarly, if at all for all the values of k system is unstable, then we call the system as absolutely unstable system. So a system is said to be conditionally stable if the system is stable for only few range of k values. For example, so let us say k is stable in between 0 and 6. So in a system, if the k value is varying from 0 to 6, then system is stable. Then if it is beyond 6 value, then system is unstable. So whenever you impose some conditions of k, system stability, then we can call it as a conditionally stable system. Similarly, a system is said to be marginally stable if the impulse response of the system is having continuous oscillations with constant magnitude. Usually it is called sustained oscillations. So then we say it is marginally stable or critically stable, or system is giving oscillatory response, or we can say the transient response is undamped. Next, so what are the ways to find the stability? We know stability definitions and also impulse responses, pole locations. Based on the pole locations also we can say what is the stability of the system. But it is not always to find the closed loop poles. It is very difficult to find the closed loop poles. Therefore, there are different methods to find the stability of the system. Let us look at what are the different ways of stability. So we can find the stability using root-Harvich criteria. Then also we can use root-locus technique. We can also use gain margin, phase margin concept. And using gain margin, phase margin, we can draw the frequency response plots like bode diagram and as well as the polar plot. And also we have Nyquist stability criterion. Then we have the impulse response. So these are the different ways to find the stability of the system. The first one, RH criteria, is your analytical method. Root-locus is a graphical method. And again, gain margin, phase margin, only calculations analytical, but when it comes to the plotting of bode and polar plots is a graphical technique. Then Nyquist criteria is a graphical technique and impulse response method is analytic technique. So these are the different ways to find the stability of the system. Now let us look at the first one, root-Harvich criterion. So before going to see the root-Harvich criterion, let us take the closed loop block diagram. So in this block diagram, we know that we have input, summing point followed by the your forward path transfer function, and H is your feedback path transfer function, and C of S is the output. Now let us write what is the closed loop transfer function. We can write very easily C of S by R of S is equal to G of S divided by 1 plus G of S into H of S. So in general, when I say stability in control system, we are mainly interested on the closed loop stability of the system. So open loop system is available. If we want to convert the open loop system into closed loop system, so we must investigate the stability of the closed loop system by closing the loop. Therefore, here I have a closed loop block diagram. Now to investigate the closed loop stability of this particular system, I need to look at the location of the poles. And for that, let us write what is the characteristic equation. We know what is characteristic equation, Q of S. So that is 1 plus G of S, H of S is equal to 0. Now 1 plus GH of S equal to 0 is the characteristic equation. We know that roots of the characteristic equation are my closed loop poles of the system. If we know the location of these closed loop poles, then we can easily find out the closed loop stability of the system. So therefore, this particular criteria, Routh-Hurwitz criteria, so it will not give you the exact location of the poles of your characteristic equation or of your closed loop system, but it gives how many roots of the characteristic equation are lying in the left of the S-plane on imaginary axis and or right of the S-plane. We know that if there are poles, one or more poles lying in right of the S-plane, we say the closed loop system is unstable. If there are repeated poles on imaginary axis, we say closed loop system is unstable. If there are non-repeated poles on imaginary, we say marginally closed loop system stability. Similarly, if you have all the poles in left of the S-plane, then we say the closed loop system is stable system. Therefore, we need not know what are the locations of the pole. If we know how many poles that are there in the right of the S-plane, imaginary axis and as well left of the S-plane, then you can easily say what is the stability of the system. That means we say whether the system is stable or not, but we cannot say whether the system is how much stable it is. It's very good stable, very bad stable, or very nearer to the unstable region. All these things we may not find, but you can find the just answer if the system is stable or not. Now, so in RH criteria, Routh-Hurwitz criteria, we have two conditions. One is necessary but not sufficient conditions, and we have sufficient conditions. So what are the necessary but not sufficient conditions? Let us take the characteristic equation in the polynomial form. So we have a Q of S is equal to, so A0 S power n, A1 S power n minus 2 plus dot 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 up to an. So there are n number of terms like this. So we have highest degree S power n. So the number of roots of this equation is n. And we can say that the number of closed loop poles also n. Now when we say necessary conditions but not sufficient, look at the first one. So this particular characteristic equation, if you closely observe, now all the quotient of this equation should have positive sign, or we can say in general should have the same sign. So all the coefficients, what are the coefficients here? A0, A1, A2 and up to An. If all the coefficients are positive or all the coefficients are negative, it should have same sign. Then we say we have a one particular condition like this. And what is the second condition? The second condition is there should be no missing terms. That means all the terms should present, A0 to An, all the terms should present. Then this is a second condition. So if the system is not satisfying these two conditions, we say system is directly unstable. But if a system is a system in the sense the characteristic equation, if the characteristic equation is not satisfying these two conditions, then system is directly, we can say it is unstable. Even if it satisfies these two conditions, we cannot say that system is stable. Then if it satisfies these two conditions, then we need to go for the sufficient conditions. So these two give us only whether system directly we can say unstable or not.